Hey you! Wanna know how to make it snow? Wanna know about object-oriented programming on Arduino? Wanna know about clean file and folder structure and easily modifiable and readable code? In this video, you'll learn a practical example of object-oriented programming in the form of snowflakes within a snowstorm. No more cats and dogs, no more foo and bar, let's get real. Hi and welcome back to Grandma's low resolution, low FPS basement. Since object-oriented programming is all about, well, objects, we first have to define what these objects actually are. Writing this down in a diagram can help. The first thing we, of course, want is a snowflake class. So we're gonna go up and search for class. Let's see if there's actually a snowflake. There actually is, very nice. Now we've got a snowflake class. Now the question is, how do we actually move such a thing across the screen or kind of give it an idea that it should behave in a spatial way? We can achieve this by creating another class called coordinate class. This will be part of every snowflake and will dictate where the snowflake is actually going. Now, of course, we want multiple of these snowflakes on the screen. So imagine we had a few more of these, and now we would group them together in another class called a snowstorm. Now all that this snowstorm has to do is update the position of each individual little snowflake. And then at the end we can give that whole information to our display. This information will then be provided via a bitmap that tells the display exactly where to put which individual little snowflake. By the way, I can encourage you to use this website as well. It's called Draw.io and I'll link it in the description. Now, how do we interpret this in the form of code? I of course will use my favorite code editor, Visual Studio Code with Platform.io. If you want to use that as well, you can check out my previous video showing you how exactly to work with Platform.io. The board I'll be using is an ESP32 AZ delivery, but you can basically use every other board that supports the Arduino-Framework. Now keep in mind that this video doesn't showcase how to efficiently use an OLED or how to get the most performance out of your board. This video is there to show you abstraction and encapsulation with object-oriented programming and a good folder structure. Now over here in main you can see that nothing is here. And we will try to put as little code as possible into main and abstract all the other things away into different files. We'll now set up the lib folder with different kind of folders organized by topic. For example, one thing we need is of course a snowflake folder. Then additionally, we are going to need a folder for our display. We could call it OLED or something else. I like to call it canvas, because it's basically what we draw our bitmaps on. And the last thing that's always useful, create a folder that is just called common for things that are shared between these little submodules. Let's start up with the snowflake. To make these little folders work, you would include a CPP file and a header file, preferably called the same as the folder above. Now I do expect you to know a little bit about C and C++, so you shouldn't be all too confused to what this is. If you are, look up the term include guard in C. Now we're going full object-oriented programming, which means we need classes. In this case, a class called snowflake. I recommend prefixing your classes with a little C underscore, so it's clear that it's actually a class and not an instantiated object yet. As always, this class has public and private methods. Public methods are callable from the outside. Private methods are only callable from within the class itself. We're now going to declare the constructor for this snowflake. Basically, what happens if you instantiate such a snowflake class? There's some general information on what our snowflake contains. For example, a speed at which it falls down from the sky, or a bitmap, which actually is the style of the snowflake. So let's include these variables here. Now you can see that it's not recognizing these types up here. That's because we forgot to include Arduino at the top. This variable will now hold the information how fast it travels down from the sky. This variable will hold how fast it is traveling across, maybe it's windy, and the next one is the pointer to the bitmap, which is the actual template for the pixels on the display that look like the snowflake. One thing's missing. Remember the diagram from before? We wanted to include a coordinates class within every snowflake that tells us where it is in a given time. So in the folder snowflake, we'll now create another file called coordinates.cpp. Now in here, we'll create another class called coordinates. Now, all the coordinate needs is an actual coordinate on our OLED display, which means we specify a variable x and a variable y. Now, we want to update the position of this coordinate, so we include an update method and some getters in order for us to get the current position of x and y. Now let's actually implement these functions in the CPP file. For that, we include the header file we just created. We first type the class name, then double colon, and the function name, in this case the constructor. In here we want to initialize a position. Now, since snow is falling down from the sky, we want a fixed value, the highest possible value for our y, and a random value for our x. You can already see that there's a problem. How do we know that we don't create a random variable that is too large for our display? Exactly for that, folders like common are well suited. So let's create a new file under common called common.h. And in here we'll include all kind of parameters that are used in between these different submodules. In this case, as you can see, I've defined the width and the height of the OLED display. In my case, it's a quadratic one. Now if we head back to coordinates, we can now include this very common file where we have access to these macros we just defined. Let's implement the other functions of the coordinate class. In update, we just want to add a given value to our internal coordinates variable, which just means that we add x pix to x and for y the same. Don't forget that we already defined x and y over here in our header file. And lastly, we want to build two little functions which return the current position. Quite straightforward. Back within snowflake.h, we have access to our just created header file called coordinates, which also means that we now can include a coordinates variable in our private variables. Be careful, since we want to allocate a new position to the snowflake every time it falls off the screen, we want to implement it in a pointer format so we can actually call the C++ new method every time. Now of course we want to translate the updating of the position to the snowflake itself as well. So let's include an update method. Remember getX and getY from before? That's exactly what this is for. Additionally, we should also add some getters to this class as well. Now we've got additional getters. One is about getting the current position. The other two are about getting the speeds of the snowflake itself. And the last one is for actually getting the bitmap connected to that snowflake. Now we can finally implement these functions. So on Snowflake-CPP, we can include our own little header file called snowflake.h. On the right here, you can see everything that we want to implement. And on the left, we'll actually implement it. Every time we want to create a snowflake, we want to give it a new position. So we update our position with a new coordinate. And every time we call the update method, we want to call the underlying update method of the coordinates class. Of course, every time you update, you want to increase the position by that amount that you specified in speed, because that's basically what speed is. Now, as always, implementing a getter is quite simple in this case. GetImage is where it gets interesting, because we have to source a bitmap from somewhere. We do have a variable called BMP, but that's just a pointer to a place that doesn't exist yet. So let's create a file that holds this pixel information for each snowflake. We're going to call it style.cpp and of course a header file. Now to convert bitmaps into actual C code, there are a bunch of useful websites which do that for you automatically. I'll link one of them in the description below. When it's done converting, you can just copy paste it into here and it should look something like this. And by the way, if you step really far away and squeeze your eyes a bit, you can actually see the design of your bitmap itself. Isn't that cool? You can add as many snowflakes as you like. The problem we have now is that we've got some global variables in here and we don't really know how to access them from other files because this is all exported in another file. By declaring the exact name given here over here as extern, you can tell the compiler that if you run across this, don't worry about it, I actually have these variables somewhere, because otherwise it wouldn't compile, because in other files it would say I've never seen Snowflake before, it's not declared anywhere. Another information given to you by such a converter website for bitmaps is the width and the height of your bitmap. In my case, one of them is 15 pixels wide and the other one is 20 pixels wide. This will be necessary for later. Now back at Snowflake, we can now start to build an algorithm which randomly chooses between one of these two bitmaps for a new snowflake. Since such a function is intrinsic to the snowflake itself, we are going to define it privately and not publicly, which means that the function has to actually be written out in the header file. I'm going to call this function assemble, as it basically puts together our snowflake. In here, we first get a random value for the speed of our snowflake at which it is traveling down. To easily adjust that, I would recommend putting it in macros and putting these macros up at the top. Now introduce a decision tree. Do we want our snowflake to be the first thing we designed or the second one? We can do that by applying a switch case. Now we want to add our bitmaps. To do that, we first have to include them here with include style. If the first case is hit, then we, of course, include our first design. Same thing for the second one. Don't forget to actually include the side length of your bitmap. Of course, we now need to actually define this variable up top. In any case, at the end, we want to transfer the speed to our local speed variable. As you can tell by this setup, our snowflakes won't wiggle around on the x-axis, just y. Congratulations, you've now successfully created a coordinates class and a snowflake class. Remember the diagram from before? We're now going to create a class that is a group of snowflakes called snowstorm. This file, of course, needs to know the snowflake class itself, so we have to include this here. Now, what exactly is a group of snowflakes, you might ask? Well, it's just an array of the class we did before. So what we can do is see snowflake, which is our class, call them flakes or snowflakes, and have an array. How many of them you want is another macro that you could specify with num flakes. And of course, the only thing we need is another update method. We leave the constructor empty. And that is because when we create a new snowstorm, then the array of snowflakes is already built into here. It's fixed and it's constant. On an actual computer, you might do this in a dynamic memory management fashion. But on a small microcontroller, it's best to keep some things constant if you can, because otherwise it will have a lot of trouble allocating that stuff and it will make your program really slow. Now, all we need to do is update each individual little snowflake. And since each of these snowflakes has its own update method, all we have to do is call that one in a loop. And that's already it. Now you might be wondering, the number of flakes is constant and we never actually delete them. Then how are they going to reappear up on the top when they disappear on the bottom? Good question. That we head back to snowflake and implement a method that is like the constructor but with an already existing instance. Let's call it re-init. It's a private method and in here we want to do three things. First we want to delete the old position, give the snowflake a new one and then give it a new style as well. You can delete by literally saying delete, then we give it a new one, and then we assemble the snowflake again with a new style. Here it's also good to keep track of how many different styles you have in order to put that in the macro. Right now in this program we've got 2 different styles, so let's put that up top. Now we need to call this somewhere on the condition that the snowflake has dropped off the screen. Since the updater is the only thing that's responsible for actually moving the snowflake around, we can add a condition in the updater that says if the snowflake reaches the lowest point on the screen, put it up top again. So if the position right now is greater or equal than the maximum amount of pixels we got on the screen, then we re-init and give the snowflake a new style, a new look, and a new life. It's good that we came back here because I'm seeing we don't even assemble the snowflake in the first place, so we should probably do that. Hey yo, can we please see something on the display already? Yeah, I know, good code structure takes some time. But finally we are now going to define the canvas class, which contains the driver to the OLED display. For this, as always, we're going to create a file called canvas.h in canvas and canvas.cpp. Now it's time to get a little I2C or SPI display and check what kind of driver it needs. We're going to include that driver as a library. In my case, it's a 128 by 128 grayscale display. It uses the SSD 1327, and I want to include that library from Adafruit. Of course, if you remember my last video, we actually have to include this in the platform.io.ini file as a library for the compiler to know that. So all you need to do is add these 2 lines here, or you can configure them with the platform.io UI. Now let's create a class called canvas. First of all, it of course needs to know what kind of stuff we want to show on the canvas, which means it needs to know our snowstorm. And then it needs a constructor. In this constructor, we intend to initialize the Adafruit SSD 1327 driver. This automatically means that we have to specify how big our display is. Additionally, we want basic functionalities like the initializing offset display, clearing, and the showing. But now for the juicy stuff. Not to make something move across the screen, we need a method that draws a little bitmap somewhere and another method that removes exactly that bitmap. So the next time round, the same method can come and apply the same bitmap maybe a pixel or 2 further down. And only this way we achieve a kind of moving motion. So what we want is a draw function that draws our snowstorm and a remove function that removes our snowstorm. Remember, our snowstorm contains a constant array of snowflakes, so we have to pass the pointer. But now let's do something very cool. There's a method called overloading, in which you specify the exact same function again with the same name, but different parameters. And from there, the function is intelligent enough to decide where you are calling it from. In our case, we can use this trick to not only have a draw method that is called draw for the whole storm, but also for a single snowflake, which makes our code more modular and more usable for other cases. The last thing our canvas class needs is of course a pointer to the actual SSD 1327 driver. Now, as mentioned before, we're going to instantiate one of these Adafruit drivers. We assign it to our pointer pDisplay, and everything in here is by Adafruit. We have no control over this right now. As you can see, it's asking for an OLED reset. With most of these libraries, if you don't want to change anything, in this case you can just type -1 and it will recognize that as I don't want to change anything. Depending on your display, you might have to do a bit of digging. Right now I'm using I2C, but you could also use SPI, but that requires some additional configuration in the header files for the Adafruit SSD 1327 library. This project may also work with other SSD types, but I haven't tested that. You may recall that most of these serial devices have some kind of begin method that is needed to initialize the hardware behind it. In our case, we call this begin method in our init, which in this case is a synonym for begin. As always, we pass the I2C address and hit begin. Since we have this pDisplay variable pointing to an actual instance of that driver, we can call it over this little pointer here. Since a few things can go wrong during initialization, there's a better method to actually catch these. If we are unable to start the driver, tell us that and just wait. This way we know something went wrong, but not on our behalf, but on something else in the background. Now for the absolute juiciest part, the quintessence. How do we actually put something that we just configured for what feels like ours on the screen? You may know that the SSD library provides a function called drawBitmap. We are going to use just that function to do everything else in this project. DrawBitmap needs an X and Y coordinate. Remember that? It needs a bitmap. We already got that one as well. It needs a width. We have that. It needs a height. We have that as well. And it needs a color. This references the grayscale display. You may have a display without any scaling, then color won't be an option here. In order to draw the bitmap correctly, we extract all the necessary information for the bitmap from the given snowflake pointer. For example, how do we get the X coordinate? Easy. We call our flake, say get the position, and from there we say get X. And that's it. Same for Y. I think you can start to see why getters are really useful in this case. Now it needs the bitmap itself. Luckily, we implemented such a method that returns the bitmap itself. So we call pflake.getImage. As you can see now, we need a width and a height for the bitmap itself. You may remember we didn't actually specify that yet, so let's do that real quick. We head on over back to Snowflake and we declare a getter for the size and we define it in the CPP file to return us exactly that variable. This is now, of course, callable in canvas.cpp. Now the cool thing is, since we implemented a draw method first for a single flake, all we have to do to draw the storm is call this draw function for the flake in a loop. In here, we specify a loop that calls each single snowflake of a storm, gives us the address to that, and then draws exactly that little snowflake. Because I'm lazy, the remove method contains exactly the same code as the draw method, but 0 as color, which basically means nothing. And of course the same applies to the whole storm. All that's left are clear and show. These are just wrappers for function the display would have anyways, but now it's clearer and more open when it's connected to canvas as well. All clear does, it clears the memory and then actually displays that, which is nothing. And show actually displays the stuff. You know which file is still completely empty? Main. So finally, after hours, let's get to main and run the program. Now first we include all the needed libraries. In this case, common, as it contains common stuff that we need, and canvas, since that includes basically every kind of stuff that we've written right now. As mentioned, our canvas object and our snowstorm object will be constant and global. These will not be dynamically allocated, these exist already. And as you know, in Storm itself, all of the 25 snowflakes also exist. And now for some magic. All we need in setup is basically an init. We clear that and we show in order to start with an empty screen. And now the loop is actual magic. Are you ready for this? All we do, we draw the storm, we show it, then we wait, then we remove the storm and update all internal positions of each little snowflake. Then it comes back and draws exactly that updated storm. Every time this delay passes, we get a little moving motion on our screen. Now, moment of truth. I'll try to compile it and see if it actually works. I don't know, man. Nice, it's working. Easy. You can now display on there whatever you like. in a clean fashion, object-oriented, with splitted files and easy to look at. And now, even if it's not snowing outside, you can have your snowstorm anytime you like. Now, if that was a bit fast or much for you, don't worry. I've included the whole code as a Git repository in the description down below.